So we're going to move on now to the next part of Apollonius's work. This, in Heath's book, covers propositions 16 to 23. These propositions develop some basic theory regarding transitions from one diameter to a different diameter in a conic section, because it might be that the diameter that we've got from the outset is actually quite an inconvenient one to work with. It might be that there is a different diameter that happens to be more convenient for us to work with. In the same way that with a vector space, for example, the given basis might not actually be the most convenient, and you might want to transition to a different basis. Remember that diameters in conic sections, they introduce kind of coordinate systems, so it kind of makes sense that we might want to do that from time to time. So I'm not going to go through every single one of the propositions. I've got three propositions in particular that I want to focus on, propositions 17, 20 and 22. I've chosen these because they specifically relate to the parabola. Not that there's anything special really about the parabola, it's just I had to choose one of the sections really to concentrate on, so that was the one that I chose. These propositions have a much more geometric feel to them than some of the earlier propositions. So what we've seen up to now has involved quite a lot of manipulation of ratio and proportions. Although there is going to be some of that in these propositions, in the proofs of these propositions, it's going to be focusing much more on manipulation of areas of elementary shapes, so particularly triangles, quadrilaterals and parallelograms. So I'm going to start off with proposition 17, which is this one, that in a parabola, similar to the one here in the diagram, which I'll explain in a second, the area of the triangle RUW, so that's this triangle in here, is equal to the area of the parallelogram EPWF, which is this kind of strip in here. The intention was with this diagram that I draw the lines that are parallel in the same colour to make it easier to distinguish them. It's clouded over a little bit, there's not so much light, so it might not be quite as easy as I anticipated to see the different colours. So here's a little key just to point out which colours are involved in here, but it should be fairly clear which lines are meant to be parallel anyway. So what we've got here is through a certain point P on our parabola, we've got a diameter, and that's this line here. So that's assumed to be a diameter. And then through another point Q on the parabola, we've got a line that is parallel, that is drawn parallel to that diameter. Okay, and then we've got a third point R on the parabola, which is, we're just going to assume for sake of argument that it's here. We draw the tangent at Q, the tangent to the parabola at the point Q, which is this red line here, which meets the diameter at the point T, and then through R we draw a line meeting the diameter in U, such that that line is parallel to the tangent through Q. And then the lines R and RW, QV are the ordinates, so they're drawn ordinate wise to the diameter through P, and extended or produced if necessary to meet the horizontal, the parallel through Q to the diameter in F. And we've also got the a line drawn parallel to the ordinates through P as well. It's important to note at this stage that this is not a tangent. We're not assuming that this is a tangent at the point P. It will actually turn out further down the line that it is a tangent line at the point P, but we're not free to assume that just yet because we haven't proved that. In the course of this, proving this particular proposition, and actually in the propositions that follow, I'm going to be assuming this proposition, which is proposition 12 from Heath's work. I'm not going to prove this, we're going to take it as given. What this says is that given a parabola and a diameter through the point P, and just any other point Q on the parabola, if we draw a line ordinate-wise from the diameter to Q, so that line meets the diameter here at V, and then if we draw the tangent at Q down to the diameter meeting the diameter in T, then TP is going to be equal to PV. So I've tried to use similar notation to what I'm using in this diagram, just to make it easier to make the comparison. We will be assuming this without proof, although it's proved in Apollonius's work and in Heath's translation. So the start point for us with this particular proposition is to notice that TP is equal to PV as shown in proposition 12, and therefore TV is equal to 2 PV. Okay, and what we can also say is that the area of triangle QTV is equal to the area of parallelogram EPVQ. So why is this? Well, if I just draw a little diagram down here just to try to illustrate what's going on a little bit. Okay, so that's T, P, V, Q, and E. Well, I know that that is the same as that, so that's what we've been getting here, the result that we've been getting from here. So what I'm going to do is I'm just going to extend this out a little bit, just kind of complete this parallelogram. So let's just say that that's X. I don't think I need to label it, but just in case. So we've got the parallelogram here, XTVQ, of which TQ is, it bisects, it's one of the diagonals of that parallelogram. So therefore, Euclid 1 proposition 34 will tell us that the area of the parallelogram is also bisected. Okay, so the area of triangle QTV is equal to a half of the area of the whole parallelogram XTVQ. Similarly, because EP is a line that bisects both of these sides and is parallel to QV and XT, then the area is also bisected by the line EP. So therefore the parallelogram EPVQ is also going to be half the area of the whole parallelogram in here, which gives rise to this equality here. Okay. Next, because RW and QV are ordinates to the diameter P, then we can say that RW squared is equal to PL, which is the parameter of the parabola with reference to the diameter P. PL times the abscissa of RW, which is PW. And similarly, QV is equal to PL times PV. So therefore, oh sorry, that should be QV squared. QV squared, the ratio of QV squared to RW squared is equal to the ratio of PL times PV to PL times PW. So the PLs will cancel, so this is one of Euclid's laws, propositions, book 5 most probably. So ratio of QV squared to RW squared is PV to PW. Okay, and now the ratio of QV squared to RW squared is the same as the ratio of area of triangle QTV to RUW. Why? So this ratio here, I claim, is equal to this ratio here. So this follows from, again, it's from Euclid, proposition 19 from book 6, which says that for similar triangles, of which QTV and RUW are similar triangles, the ratio of their areas is the same as the ratio of the squares of their bases. So think kind of along the lines of linear scale factor and area scale factor kind of thing. If we take as their bases respectively QV and RW for these triangles, then the squares in their bases, QV squared, RW squared, is the same as the ratio of their areas. So also from Euclid's Elements, book 6, proposition 1, tells us that the ratio of the areas of parallelograms under the same height is the same as the ratio of their bases. So the parallelograms EPVQ and EPWF are under the same height. So this height here between the two horizontal blue lines in the diagram. So therefore the ratio of those two parallelograms is going to be the same as the ratio of their bases. Well, their bases are PW and PV, which is the ratio that we've got here. So therefore this thing here, PV, the ratio of PV to PW, is equal to the ratio of the area of parallelogram EPVQ to the ratio, to the area of the parallelogram EPWF. And because originally we had that the ratio of QV squared to RW squared was equal to the ratio of PV to PW, and this ratio is equal to this ratio is equal to this ratio, then these two ratios must also be equal to one another. But we also know from what we've proved here that the area of triangle QTV is equal to the area of this parallelogram here, EPVQ. So these two are equal to one another. So that means that for these two ratios to be equal, then these two must also be equal. So we conclude that the triangle RUW is equal to parallelogram EPWF, which is exactly what we wanted to prove. Okay, so moving on now to the next proposition, proposition 20, that I want to go through. The proposition says that in a parabola, the straight line drawn through any point parallel to the diameter bisects all chords parallel to the tangent at the point. So in the diagram here, we've got our parabola, and this line here, the blue line, if you can see that it's blue, that is, through the point P is our diameter. So that's the diameter that's referred to in the statement of the proposition. Through another point on the parabola Q, we draw a line that's parallel to that diameter through P. And in addition to that, we draw the tangent line to the parabola through the point Q, which meets the diameter through P at the point T. And then we choose a third point on the parabola, an arbitrary point R, and we draw a line through R parallel to that tangent line through Q. So that's this second red line here, which will meet the parabola again at R primed, and it will also meet the diameter at the point U. Okay, and then through R, Q, and R primed, we draw lines ordinate wise to the diameter through P. So QV is an ordinate, a line drawn ordinate-wise to Q, RW, and R primed, W primed. And if we produce these lines if necessary, so we get the intersection with the line drawn parallel to the diameter through Q, and we get the relevant intersections here. In particular, we've got, actually it's not to do with the ordinates as such, but the line R primed will intersect that parallel to the diameter through Q at the point M. This is going to be an important point for us to focus on in the proof of this proposition. We've also got the parallel drawn through P to the ordinate lines that we've just drawn through R primed, Q and R. So just like in the previous proposition, it might look like this is a tangent at the point P here. In a way, that's kind of what will follow from the proof of this proposition, but we're not in a position yet to actually to assume that. So as far as we're concerned, it is just a line drawn parallel to these ordinate lines. Okay, so with this one, the start point is using what we've just proved in proposition 17. We can say that triangle RUW, the area of triangle RUW is equal to the area of the parallelogram EPWF. Similarly, we can say that triangle R primed U W primed is equal to parallelogram EP W primed F primed. So both of those follow immediately from proposition 17. And then if I subtract this area from this area and this area from this area, what I'll get is, well, you can see straight from the diagram, RUW, take away this little triangle down here, I'm just going to be left with this quadrilateral R primed, W primed, W. And on the other side of the equality, I've got the parallelogram EPWF, and I'm taking away EPW prime F prime. That's going to leave me with the parallelogram F prime W prime WF. So F primed W primed WF. Okay, and then each of these areas of these shapes has a kind of an overlap. Okay, so if I just draw a diagram just to emphasize really what I'm talking about here. So let me try to get this right. So F primed W primed FW, and what else do I need? Quadrilateral R primed, so R. So we've got the quadrilateral R primed in there. So R primed, W. So that quadrilateral and the parallelogram F prime, W prime, WF have this common area here. Okay, that's M. So I'm going to subtract this common area from both of these. So that would be this shape M R primed, W primed, WF. So what I'm going to be left with in that case is here triangle RMF, and over here I'm going to be left with triangle R primed MF primed. Okay, and it's quite clear, I think, from the diagram, considering the parallels that are involved, that these triangles are going to be equiangular. They're going to be equiangular triangles, so therefore they're going to be similar triangles. But not only do we know that they're similar, they've actually got the same area. So that means that actually they're congruent. So triangle RMF is congruent to triangle R'MF'. This itself is not sufficient to tell us that the triangles are congruent, because two triangles could look very different to one another and still have the same areas. But looking at the parallels involved, we can see that the triangles are at least similar because they're equiangular, and this, coupled with this, tells us that they're actually congruent. So if they're congruent, RMF and R primed F primed, then RM and R primed M are corresponding sides of those two triangles, so they must be equal. And this proves the theorem, or the proposition. Why? Because it means then that this line through Q, which was drawn parallel to the diameter, bisects this chord R primed. Now, if you remember what the definition of a diameter is a line, any line, that bisects a family of parallel chords. So this line bisects the chord R primed. That itself doesn't mean that it's a diameter, but when we consider that R was an arbitrary point, so this would work for any chord drawn parallel to QT, then we can see that any such chord would actually be bisected by this line through Q, which was drawn parallel to the diameter. So the upshot of this is that every line drawn parallel to the diameter in a parabola is again a diameter, and the lines that the chords that new diameter is going to bisect are the chords that are parallel to the tangent at the point of intersection of the new diameter with the parabola. We can also apply that to what's going on down here at P. We said originally that the line PE can't be assumed to be a tangent, but it turns out that it is, because the line through P is a diameter and it bisects these chords. If we were to extend these chords, then they would all be bisected, so therefore they must be tangent to they must be parallel to the tangent at P. Well, they're parallel to this line PE by construction, so therefore PE must itself be a tangent. So that proves the theorem. This is going to be used in the next proposition, which I'm going to move on to now. Okay, so moving on to the next proposition. So this is proposition 22 in Heath's translation of Apollonius's work. We've got exactly the same diagram as the previous proposition. The only difference is now we know that this blue line through Q is going to be a diameter by what we proved in the previous proposition, and we also know that this line R through R primed parallel to QT is going to be a chord to that particular diameter. So what we want to prove here is that in a parabola, so similar to the situation that we've got here, if this equality holds between these two ratios, so this lowercase p here, then this equality will result. Now, what's the significance of this? Why should this be important? Because it seems like a kind of random equality that's being proved. But this is really significant because if this is the diameter, this blue line through Q is a diameter, and this is one of the chords R primed is a chord that's bisected by that diameter M, then that means that MR is an ordinate to that diameter and QM is its abscissor. Now, if you remember, for a parabola, the kind of characteristic defining relationship for a parabola is that the square on the ordinates is equal to the abscissa multiplied by the parameter. Well, that's what we've got here. We've got the square on the ordinates is equal to the abscissa multiplied by this number p. Well, that means that this lowercase p can only be the parameter of this parabola. It's because it's unique. The parameter of a section with reference to a particular diameter is unique, so p must be the parameter. So what this does is it allows us, given other information obviously about the parabola, we can actually find the value of the parameter of with reference to a particular diameter. Obviously this could all be changed around so that this was relating more to diameter p, but in this particular proposition we're picking on q, this diameter through q. Okay, so where do we start with this one? Well, first of all we need to notice that this EPVQ is a parallelogram. Okay, so what that means is that EQ is equal to PV. And by proposition 12, which I haven't proved but I've mentioned is something that we need to assume as having been proved, then TP is equal to PV as well. Okay, so in particular we're interested in the fact that EQ is equal to TP, because notice that triangle TOP is similar to triangle EOQ. Because they're equiangular, it's quite obvious that they're equiangular. These angles are going to be the same, these angles are going to be the same, and these angles here are going to be the same. So not only that, they've got equal bases. So that means that they must actually be congruent, and therefore the area of triangle TOP is equal to the area of triangle EOQ. And what we're going to do now is we're going to add to both of these the area of this shape QOPWF. QOPWF. So adding QOPWF to TOP is going to give me this shape in here, QTWF. So it's quadrilateral QTWF, and adding QOPWF to triangle EOQ gives me this parallelogram in here. So parallelogram EPWF. Okay, now by proposition 17, parallelogram EPWF is actually equal to triangle RUW. So quadrilateral QTWF is equal to triangle RUW. So now from both of these we're going to subtract MUWF. So that's quadrilateral MUWF. So QTWF minus MUWF just leaves me with parallelogram QTUM and that's going to be equal to RUW minus MUWF, which is triangle RMF. Okay, so I just need to do a little aside calculation now. If I just draw this diagram here, so try and draw it as best as I can. So that's M, F, R, Q, T, and U. So I know that these two areas are equal, the areas of these two shapes. So what I can do is I can bisect RM at the point X and form a parallelogram. I'm not bothered what this point is really over here. And moreover, the area of this parallelogram now is equal to the area of this parallelogram here. And also these parallelograms are equiangular. Opposite angles in a parallelogram are equal, and this angle has to be equal to this angle here, so that angle has to be equal to this angle. And similarly, angle TQM has to be the same as MUT, which has to be the same as MX, whatever this is here, and this angle here. So they're equiangular. And from that, we can say from Euclid's 6:14, so Euclid Book 6, Proposition 14, says that in equiangular parallelograms that have equal areas, their sides are going to be related. They're going to be inversely proportional. I can't remember the exact statement, but it means that QT to MF, the ratio of QT to, sorry, not to MF, no, to XM, sorry, is equal to the ratio of MF to QM, or MQ. So therefore, MF times by XM is equal to QT times QM, but XM is half of RM, so MF times a half RM is equal to QT times QM. So therefore MF times RM is equal to 2 QT times QM. So therefore this equality implies that we have this, that MF times RM is equal to 2 QT times QM. Okay, now by similarity, I know that, for example, the ratio of RM to FM triangle RMF is similar to triangle OQE, so therefore the ratio of RM to MF is going to be equal to the ratio of Q to QE. But by hypothesis, this is equal to P ratio to QT. Okay, and then using a little bit of manipulation of the ratios here, I can say that Rm squared, the ratio Rm squared to Rm times Fm is equal to P times Qm to Q, what do I want? Sorry, 2 Qt times Qm. But this and this are equal. So I can't remember the exact proposition in Euclid, but it says that if the ratio of if you've got two magnitudes A and B and their ratio with respect to a third thing C, so this is a little aside, so two magnitudes and their ratio with respect to a third, they're equal ratios, then A and B must have been equal. A equals B. So I can't remember the exact number of the proposition. I imagine it'll be in book 5, somewhere in book 5. So that means that Rm squared must be equal to P times Qm, which is exactly what we wanted to prove up here. Something that came to mind as I was preparing this video, as I was going through the Apollonius' solution to proposition 22 that I've just covered, is how did Apollonius know to choose this specific relationship as part of the statement of that proposition, proposition 22, in order to show that this P was actually going to turn out to be the parameter of the diameter of that parabola that was involved. So obviously we can never know the definitive answer to this. It's not as if we can just go and ask Apollonius what was going through his mind. One explanation obviously might be that Apollonius was just such a great geometer, such a genius, that he was able to see that this was going to lead to that, and he was able to see things clearly enough in order to just start with this and get to the desired end point. It wouldn't be surprising. Apollonius is considered to be one of the greatest geometers, certainly in ancient Greece, and possibly one of the greatest geometers of all time. So it's entirely plausible that that's the case. But there is another explanation, which I think could be more plausible, although whether it's actually the case is an entirely different question, and that is it's more to do with what Apollonius might have deliberately left out of his work. What we see in Apollonius's work and in Heath's translation of it is what's called the synthesis of the problem. So Apollonius starts with this as part of a particular statement, the proposition, and then he goes through a series of logical deductions to get to the desired endpoint, which is that P is the parameter. But often when you read ancient Greek geometry, before the synthesis, which goes in that direction from here to here, you'll see something called an analysis. So what an analysis is, it's not exactly the opposite to a synthesis, but what you do with an analysis is you start at the desired endpoint, obviously without knowledge of, in the case of proposition 22, without knowledge of this. You start with this. This is what you want. You want the parameter of that diameter. So you can assume that it's done, that you have actually somehow achieved that. And then you can go through a series of logical deductions from that point and see where you end up. So one possible endpoint is that you get to a result that clearly contradicts something that's well known to be true. So you might get to a particular, starting from this, you might get to a particular endpoint that contradicts the statement of Pythagoras' theorem. So it might say that Pythagoras' theorem is somehow valid in a non-right-angled triangle. Which, in that case, that shows that what you've originally assumed is wrong. There's no point in trying to make it into a conjecture, no point in trying to prove it. It's impossible to do. On the other hand, what can happen is that you, by going through this series of logical deductions, you get to a certain endpoint that is entirely consistent with everything that you know, and which is a kind of a simple enough statement that it can actually form the basis of a proposition in order to prove that start point of the analysis. If you, it's almost like reversing the steps, so to speak. So what might have happened is that Apollonius has started with this, so P is the parameter, and he makes a logical deduction from this to get A, and then he makes another logical deduction, B, and this goes on, and he gets to X, and then finally we get to this OQ to QE is equal to whatever. Okay, and this is the analysis. And let's say Apollonius realizes that this is entirely consistent with, this is entirely feasible, there's nothing wrong with this, there's nothing preventing this from actually occurring. Well, this then forms the basis of the proposition in order to try to get back to this. So it's maybe not just this, there might be other assumptions that are included with it. So what you can do, if you're lucky, you can just change the direction of the logical steps. You can reverse all of the steps and get back to here. That's fine if all of the steps are, the logic is bidirectional at each stage. But what's more likely to be the case is that you're going to hit a bit of a hiccup at some point along the way. So let's say, for sake of argument, that we can reverse that step, we can reverse that step, and we can reverse that step, but then we get to this point and there's a problem. Because A implies B doesn't necessarily mean that B implies A. But I want to reverse the logic, but to do that, it might be that I've just got to introduce a new assumption somewhere. So let's say in here I put new assumption, and this will get bundled in with all of the initial assumptions in the statement of the proposition. And B coupled with this new assumption means that actually I can reverse that step. And let's say I don't have any problems reversing that step. Well, now this is the synthesis of the problem, roughly speaking. So we've got the condition that's come about from the analysis, and we've got this new assumption all bundled in there. So this is a possible reason, a possible way that Apollonius could have come up with this. Obviously we don't know. Another question is, why would Apollonius not include this in his work? Because sometimes he does in some solutions, but sometimes he doesn't. And it might be just personal preference, it might be that he didn't see the need to include a particular analysis, maybe it disrupts the flow of the book, but there might be other reasons. So sometimes some geometers were very protective of the knowledge that they acquired, that they obtained from their work, particularly when it came to geometry and numbers, and they might actually want to hide the techniques that they've used to get to particular results, leaving out the analysis, maybe to a more run-of-the-mill geometer at the time. This analysis technique wouldn't have been widely known necessarily. So withholding that bit of information means that it seems much more impressive, this result that's been obtained. It seems that it's been obtained through superior intellect, as opposed to just kind of poking around and just hoping for the best. This technique of analysis is effectively a theorem or proposition generating procedure by starting at the end point and in effect working backwards to a start point. Then that gives you basically the statement of your proposition. but it does mean that you've got to, there's a lot of trial and error, there's a lot of poking around. Sometimes you'll try things and it won't work, sometimes you'll try things and it'll work perfectly, but it is a bit of trial and error. But withholding that bit of information might have given it a bit more of a mystical feel, and had a bit more of an impact on people that didn't know about this particular technique. Obviously we'll never know. So I'm going to finish this video there. In the next video I'm going to finish up with Apollonius's book 1. I'm going to move on to book 2, and thank you for watching this video, and I look forward to seeing you in the next video.